Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Okay, let us continue our discussion on dislocations. In the last class, we looked at detailed geometry of dislocations and types of dislocations, and we also looked at the energy of dislocations. Okay, and in this lecture, we will see stress fields around the dislocations. So if you look at the slide, what is shown here on the left hand side is a very nice image, which clearly shows that the extra half plane is there, and then there is a dislocation, the positive edge dislocation, and then you see that second half of the lattice, and there is some, like in the previous slide, I showed some shade. This green shade nicely gave some kind of a stress field around the edge dislocation. What you have to appreciate here is this, the extra off plane, this particular, the above which the stress field is quite different compared to the bottom of the edge dislocation. That is, the above planes, the above off, I would say, will experience a compressive stress. Okay, and the bottom half experiences tensile stress. Okay, and it's not that simple. I mean, we have just nicely shown in the picture like this. But if you get into the details, it is much more interesting to note that contours of the stress fields are shown here, and it is not simple compression, simple tension. It is hydrostatic stress. So you know the meaning of hydrostatic stress now, because we have enough background for that. So the above one is hydrostatic compression and the bottom one is hydrostatic tension. Okay, and we will now see that how complicated it becomes when it comes to the edge dislocation stress fields. Okay, as compared to screw dislocation, right? So around a dislocation, the atoms are displaced from their normal position. These displacements are equivalent to the displacements caused by elastic strains arising from the external stresses. So to describe these stress fields, and then this is a coordinate we are choosing, and this is a reference, and you can see that it's a polar coordinates. So this coordinate system for describing a location near a screw dislocation, the dislocation is parallel to z-axis and at a distance r is equal to 0. So it is parallel to z, so the r component is 0 there. The equations given here assume the isotropic elasticity. For a screw dislocation with a Burgers vector b parallel to z-axis, these are the shear stress tau in polar coordinates. Shear stress we know, Gv by 2 pi r. This we have already seen this one. But since it is tau r theta and tau r z, which is equal to sigma r, which is equal to sigma theta, which is equal to sigma z, is equal to 0, because r is 0, where g is the shear modulus and r is the radial distance from the dislocation. The minus sign indicates that the repulsive force is inversely proportional to the distance between the dislocations. So we are talking about the repulsive force of the dislocation. We will in a minute we will see what are the detailed forces. So the above equation indicates that the screw dislocation creates no hydrostatic tension or compression, because the hydrostatic stress is defined like this: sigma r plus sigma theta plus sigma z by 3. So here we are talking about r is equal to 0. Therefore, there should be no dilatation or volume strain associated with a screw dislocation. However, real crystals are elastically anisotropic. Please, we have to remember the equations, whatever we show here is through isotropic elasticity, and in a real-time crystal system, we will have elastic anisotropy. Okay, this may not strictly valid, and then we may require some special expressions so that it will describe the elastic modulus with respect to each direction of the crystal orientation or atomic density and so on. So there may be a small dilatations associated with the screw dislocation in real times. That's what it says. For an edge dislocation that lies parallel to Z and that has its budget vector parallel to X axis, then the situation is slightly different. So the shear stress is defined like this in a Cartesian coordinate. Okay, and what you see here is there are two normal stresses, right? Sigma x and sigma y, and the shear stress. All of them are there. And you notice that there is another sigma, that is a third normal stress, also exists in this case of edge dislocations. Okay. So we are not getting into the details of how to derive these equations. My intention of bringing here is to give an idea that the stress field around the edge dislocations are quite complicated. Okay, it's quite complicated. That's the idea. And then all these equations supports that. We will also go to visual impression on how the stress distribution around these dislocations are perceived. Okay. So here, where x and y are the coordinates of the dislocation as shown in the figure, where the d is gb by 2 pi times 1 minus mu. This I have already told in the previous class. Whenever you are talking about edge dislocation, you have to look at this elastic constants. This 1 minus mu term comes because this is treated as a plane problems, and especially plane strain problems. Okay, you just go back and verify what is that we have derived for plane stress and plane strain conditions, the different elastic constants we have derived, and you will be able to appreciate this. One of the important features of these equations is that there is a hydrostatic stress, sigma h. This term also you know. In the earlier classes we have seen sigma x plus sigma z by 3. This is in a Cartesian coordinate around an edge dislocation. So the hydrostatic stress can be written like this by the previous expressions, what we have for sigma x and sigma y and sigma z, and where A is the GB times 1 plus nu divided by 3 pi 1 minus nu. So there is a hydrostatic compression above the dislocation, edge dislocation, that is positive y, and hydrostatic tension below it. This is what we have already seen it. And what I'm trying to show is another nice illustration of how the stress fields are distributed among around this edge dislocation. So all of you know this notation now, the way of representing a shear stress in the strength of material notations. We have already discussed this, how the shear stress and how positive shear stress is symbolized like this, or negatives. This is positive, this is negative. So what we are trying to do by showing this here is, as such, we said that there is a hydrostatic compression and hydrostatic tension here. When the stress fields are too complex like this, how this dislocation will respond to the external stimuli. For example, a stress within the crystal itself, how it will, what type of stress, whether it is a positive sign or negative sign, okay, whether it will attract or repel, or will just annihilate, or it will just come to an equilibrium, or it will further increase the energy. So all these questions can be answered, or at least you can at least make an attempt to correlate, make an attempt to interpret, right? This will help. So that is the reason. So if you look at this, yeah, this is a coordinate system. We'll try to now explain this. The dilational and shear stresses and the signs of these stresses are illustrated here. Okay, so you know the shear stress, this is positive and this is negative, and again this is all compressive, right? You can look at the normal stresses, they are in compressive mode, and here again biaxial, and this is tension, this is compression. In this direction it is tension, this is compression, this is positive shear, this is negative shear. So what is the net? That is what is shown here. The sense of shear stress tau xy and the dilatational sigma x and sigma y stresses components of finite dislocations. So we will come back to this diagram in a minute, where we exactly see what this particular stresses will in each quadrant, how they are going to behave. In this quadrant, is it going to behave completely tense, tension, or what kind of an effect it will create to an external force or external object? Either it is going to attract something, or whether it is going to repel something, what kind of force it is going to exhibit in each quadrant. That will also give you much more idea. We'll come back to this diagram. Okay, there are no shear stresses acting in the direction parallel to the dislocation line. That means dislocation line, you know, this is a line which is going through this perpendicular to this plane of this image, and there is, however, a third dilational stress normal to the plane of the figure. There is no shear stress, but there is a normal stress. This is what we have seen. Okay, the stress field around the dislocation tells us something. What is this image shows? This image shows the lining up of this edge dislocation one over the other. Please remember, we just described that the extra half plane, wherever it is there, it is hydrostatic compression, and below that hydrostatic tension. And when the dislocations are lined up like this, what can happen? So you should just so the forces of compression and tension, they try to align together. So that is why this kind of alignment is possible, which is also called a low angle boundary. Okay. So that dilatation causes interaction between the edge dislocations. Given sufficient mobility, edge dislocations of like signs tend to form walls with one dislocation directly over the other as shown. Okay. So there is an interaction of this edge dislocation with the like signs, that is same sign here. That's what we have shown here. They try to form a wall. Okay. The hydrostatic tension caused by one dislocation is particularly annihilated by the hydrostatic compression of its neighbor. So So this is compression and this is tension. So it goes, just aligns. Very interesting, right? So the relatively low energy and therefore stable configuration forms a low angle grain boundary. Very important idea. Okay. See, looking at the stress fields around the dislocation already gives you a perspective of how the boundaries forms. And if at all, if it forms a boundary, whether it is going to remain same or not, we are getting some idea already, right? And because of the stress field around this dislocation. And what are the other aspects of this? So you have the dislocation like this, and it has got hydrostatic compression and tension, and it can attract large solute atoms below this and small solute atoms above this. In solid solutions, the solute atoms that are larger than the solvent atoms are attracted to the region just below the edge of dislocation, where their larger size helps relieve the hydrostatic tension. So the larger atoms in a solid solution, larger than the solvent, will come here and that relieve the hydrostatic tension. Very important idea, right? And solute atoms that are smaller than the solvent atoms are attracted to the region above the edge. So here, hydrostatic compression region. In either case, edge dislocation will attract solute atoms. Very, very important point or metallurgical point of view. Okay. So edge dislocation attracts solute atoms because of the complex stress field around it, not the screw dislocation. In interstitial solid solutions, all solute atoms are attracted to the region just below the edge dislocation where they help relieve the tension. For example, the classical example is iron carbon system, where the carbon is an interstitial solid solution, right? Forms an interstitial solid solution. So carbon is an interstitial there, and it goes and gets settled here. Okay. So now we look at the forces. What are the forces on dislocations? When I say forces, there could be several possibilities. Either it is applied load or the stresses stored in the crystal itself, and what these stresses will have an influence on these dislocations. A stress in crystal causes a force on dislocation. What kind of force? Suppose if you take a plane like this and there is a dislocation line, and this is a Berger vector, the dislocation line of the length L, and the shear stress tau is being applied. So then what happens? The shear stress tau acting on that plane will cause a force on the dislocation per unit length, that is FL. So when we measured the energy also, we measured the energy per unit length, right? So here again, force per unit length, FL. Okay. Because dislocation we are measuring in length. So FL is equal to minus tau dot B. That is the force. Note that a dot product is possible here because once the plane of the stress is fixed, the stress can be treated as a vector, as a force, a vector. Here is a force. The stress tau may result from a stress field of another dislocation. So it could merely by an stress field of other dislocation as well, not necessarily an applied stress, right? So if you consider two screw dislocations, exert an attractive force on each of other, then the force will be FL is equal to minus G B1 dot B2 divided by 2 pi r. So what is that we are now doing additionally? We know that G by 2 pi r, we know that term already. The new term is B1 dot B2 because we are considering two dislocations, the stress field of one dislocation, how it influencing the other. The minus sign means that they repel one another if the dot product is positive. That could be a possibility. So each dislocation, we are now saying that the way in which it is represented, right? It is in a positive dislocation or negative dislocation. If the positive come together, what happens? The positive negative come together, what happens? Positive come together, what happens? There are possibilities, right? So if they repel one another, if the dot product becomes positive, then it is denoted by the negative sign. An equivalent statement is two dislocations repel each other if Frank rule predicts that their combination would result in an energy increase. So what is Frank's rule? Frank's rule is, you know that the energy of the dislocation is proportional to B square. That's what we have seen in the last class. Suppose a dislocation can dissociate, or two dislocation, partial dislocation can combine to form a new dislocation, or a unit dislocation can split into two partial dislocations. But this can happen only when the energy is favorable. That is what the Frank rule says. So what does it mean? Suppose if the unit dislocation want to dissociate into two partial dislocations, the energy requirement is, suppose the unit dislocation's Berger vector is B1 and the two partial dislocations B2 and B3. Then B1, there is a condition for the dissociation is both sides should be balanced, right? One side should be favorable to this energy, right? We will see some of the examples. When I show some examples, then it is easier. Okay, so that's what the Frank rules says, right? Okay, if the angle between B1 and B2 is greater than 90 degrees, then this is the condition for the dislocation reactions. B1 plus mod of B1 plus B2 should be greater than mod of B1 plus B2. The interaction of two parallel edge dislocation is somewhat more complex. This we can now see why it is. The stress field around the dislocation, edge dislocation itself is too complex. Then the interaction between them, definitely much more complex. The shear stress field for one edge dislocation that lies parallel to Z with the Burgers vector parallel to X is given by the equation. This is the same equation what we just seen in the couple of slides before. Shear stress. The mutual force on that plane will be of this nature. Okay. See, earlier we just looked at the stress field alone, but now we are talking about two dislocations coming together. Okay, parallel dislocations. That's why we come to two Burgers vectors and dot product. For the dislocation with like sign, that means the dot product is greater than 0. There is a mutual repulsion in the region X greater than Y, and it will be an attraction in the region if X is less than Y. How do we understand this? Like I said, when I showed an image which shows all the complex stress field states, I said we will come back to this. We are now going back to this diagram and in different form. So if this is equivalent to saying that there is a mutual repulsion if the Frank rule predicts that a reaction would cause an increase of energy, and mutual attraction if it causes a decrease of energy. So we will qualify these statements. What are these statements? Okay. So now you look at this image much more carefully. We'll spend some time on this, and then this is exactly a similar diagram what we have shown few slides back, right? So what we have just divide them into 4 quadrants, and each quadrant also has been bifurcated with some straight line here, right? So what does it mean? So in the initial description, we said that the top half is the hydrostatic compression, okay, and the bottom is hydrostatic tension. So within that, we have now some classification, okay. If x is equal to 0 or x is equal to infinity or x is equal to y, in all these cases, the stress is 0. You can see that x is infinity, x is 0, x is equal to y means you have to travel in this line. The stress is, the force is 0, right? Any value other than these 3 will have some influence, okay. Suppose if the x is greater than y and y is greater than 0, then it is repulsion, okay. So in this region, right? But if the y is greater than x, greater than 0, then it is an attraction. So within the quadrant, you have 2 scenarios. One is repulsion, another is attraction. So this is between the 2 dislocations, right? The attraction. The stress field is like that, but in order, if another dislocation comes, then we have to see. And that is where the Frank rule helps, whether we can consider the energy, whether that will dictate whether that kind of a combination of dislocation will be stable or not. So this is just a stress field around the dislocation, okay. But you have to just, if another dislocation is coming, then that is where the Frank rule helps in terms of energy. That is how you have to look at it, okay. We will see some examples. The stress tau xy is 0 at x equal to 0, x equal to y, or x equal to infinity. Between x equal to 0 and x equal to y, tau xy is negative, indicating that the stress field would cause attraction of edge dislocations of the same sign to each other. So here we are talking about specifically the another dislocations, right? So it could be here dislocation interaction, but the same stress field is also will act on a second phase particle also, not necessarily a dislocation. But here we are giving a dislocation description. But you can also later you will see that this stress field also will be useful in explaining how it interacts with the second phase particle. Yes. Therefore, edge dislocations of the same sign tend to line up one above the other, as shown in the figure before. What is that before? That I have shown the low angle grain boundary, how it forms, and that is also because of this attraction, right? For x is greater than y and the stress tau xy is positive, indicating that the stress field would tend to repel another edge dislocation of the same sign. So it is like opposite to the previous case. So this is correspond to this quadrant, this region. The above statement one is the first one. No, attraction, this is repulsion. So for just for a clarity, I want to just So what I want to tell you is excuse me. Sorry. Yeah. So you just try to compare that diagram with this, then it will make much more sense to connect what is this symbols indicate, and then how those attraction and repulsion and attractive force, you can put one side by side, and then you will be able to appreciate this. So what each symbol means, that will be very clear. That's why I just want to tell you.